Hello and welcome to part 3 of electromagnetism. In this one we'll be looking at Faraday's experiment again and showing how we can use it to derive the equation that governs the behaviour of inductors in circuits. We'll start by going back to Professor Meloch's YouTube clip demonstrating Faraday's experiment. We have a coil of wire here and a bar magnet which he is about to push through the coil of wire. The coil is connected to this ammeter. You can see that when he moves the bar magnet, the ammeter registers a current, and when the bar magnet is just held stationary, it doesn't. The speed at which he moved the bar magnet was proportional to the amount of current that was flowing. And this was Faraday's famous experiment and the source of the information which he used to derive his famous law. That the electromotive force, as he called it, we can think of it just as a potential difference, is proportional to the rate of change of the magnetic field. We can combine this with Ørsted's experiment and realise that we now have two interesting and related effects. Varying a current produces a varying magnetic field. You don't need a current to be varying to produce a magnetic field. A constant current will produce a constant magnetic field, but if you vary the current, then the magnetic field will be varying. And Faraday showed that a varying magnetic field produces an electromotive force, which we can think of when we do circuit analysis as a potential difference. So, we have this expression that this electromotive force, if you like, the voltage across a coil, is proportional to the rate of change of the magnetic field. Now, you may have noticed that I've written B here to represent the magnetic field, whereas in the previous talks I've used H. And I called that the magnetic field as well. And yes, both of them are referred to as the magnetic field, but they are slightly different. I'll talk more about the difference between them in the next of these videos. For now, the important thing is that in many situations we can assume that they are proportional to each other. They're not equal, but they're going to be proportional to each other. And that's good enough for now. We know, therefore, that if the B field is proportional to this H field, and the Biot-Savart equation told us that the H field was proportional to the current, then if the EMF is proportional to the rate of change of the B field with time, it must also be proportional to the rate of change of current with time. The constant of proportionality in this equation is known as the inductance. And that is the equation which governs the behaviour of inductors. In order to develop a component with a large inductance, therefore, what we need is something which generates a large EMF for a small rate of change of current. One of the ways that we can do that is to have an awful lot of coils. The more coils we have in our spiral here, the greater the H field that we will have for a certain amount of current flowing through. Another way we can increase the inductance is to look at this equation. B is proportional to H, and try and make the constant of proportionality in that expression as large as possible. And we'll look at ways to do that in the next video. And this is just a reminder of what inductors look like and what they do in circuits. The key rule about inductors in circuits is that you cannot change the current through them suddenly. They really try to resist any sudden changes in current. So, the current flowing through this circuit just before the switch is closed is 0. so the current flowing through this circuit just after the switch is closed will also be 0. And if there's no current flowing through this resistor, there will be no potential difference across this resistor. Therefore, just after the switch is closed, the EMF, the voltage across the inductor, will be equal to V0. However, place a voltage across an inductor and the current will be changing. di dt will be E over L. And if there's a voltage across the inductor and it has an inductance, the current will be changing. And the current will start to increase through this inductor. That's all for this time. Next time, as promised, we will look in more detail at the difference between the B field and the H field and see how they are related and what techniques we can use to maximize the value of inductors.